Assalamu alaikum, my dear students. Uh, I think today we will start the final topic of our syllabus on solid state physics 1, and this is from chapter number 9 in Kito, third edition. And let me display Kito. I think it's not third edition, it is the 8th or 7th edition. Let me show you which you already have. Yeah, this is the one, and this is chapter number 9, and we will talk about few topics in the early pages of this chapter. The title of the chapter is Fermi Surfaces and Manifolds. Let me first introduce the various zone schemes which are used in solid state physics. We have a reduced zone scheme, then we have the periodic zone scheme, and then we have the extended zone scheme somewhere written here. So what are these schemes? I think in chapter number 2 we read that all the wave vectors which lie outside the first Brillouin zone can be brought back into the first Brillouin zone using the reciprocal lattice vectors, and these vectors are equivalent to each other. So on the basis of this, we have designed a reduced zone scheme. Here is this reduced zone scheme in figure B, in which we have taken the energy versus K graph, and we have taken the part of the graph which goes outside the first Brillouin zone, as you can see here, into the first zone by transferring, for example, this part to this part. This is the part equivalent to this, and we have reduced this into the first zone using the negative of a reciprocal lattice vector. Similarly, all the parts of the energy versus K diagram, as shown in the extended zone scheme over here, have been reduced into the first zone, and this is known as the reduced zone scheme. The extended zone scheme is the normal scheme, and then we have the periodic zone scheme, in which we have taken each part which lies outside the first zone, and we have transferred this part to each of the other zones, second zone, third zone, fourth zone, etc. And this is the periodic zone scheme. You can go through the description given in the early pages of this chapter to understand this topic. Okay, so that was about the zone schemes, and it is summarized over here. The extended zone scheme, in which different bands are drawn in different zones in a wave vector space. The reduced zone scheme, in which all the bands are drawn in the first Brillouin zone. The periodic zone scheme, in which every band is drawn in every other point. So this was the various zone schemes. Now let us come to the Fermi surfaces and the construction of Fermi surfaces. You have so far felt the significance of the Fermi surface, because this is the surface which determines the properties of a solid, all sorts of properties. You know what is a Fermi surface, and once we understand that Fermi surfaces are so important in predicting the properties of a given solid, So we got to know how can we construct the Fermi surfaces. So let me go through this description over here. We consider in figure 5 the analysis for a square lattice. The equation of the zone boundaries given by this equation and is satisfied if K terminates on the plane normal to G at the midpoint of G. Let me show you this figure, the figure 5. This is the figure 5. So here is a square lattice, and we have shown few reciprocal lattice vectors in the reciprocal space, and with reference to this figure we are going through this description over here. The first Brillouin zone of the square lattice is the area enclosed by the perpendicular bisectors of G1. So G1, the perpendicular bisectors of this type of vectors give us the first Brillouin zone as shown here. So this is the first Brillouin zone. Okay. These four reciprocal lattice vectors are described by these equations. The second zone is constructed from G2 and the three vectors equivalent to it by symmetry. So for the first zone we use the nearest neighbors, for example this point being the central reciprocal point, and this is the shortest reciprocal lattice vector connected to the immediate neighbors. So this is the nearest neighbors, this one, this one, this one, and similarly this one. So these are the nearest neighbors, and they correspond to the reciprocal lattice vectors like G1. Now the next nearest neighbor is this one, this one, this one, and this one. So based on the next nearest neighbors we have the reciprocal lattice vectors like G2. So these G2 make up the second Brillouin zone as shown by this square which I am scanning. So this square is the second Brillouin zone. So what we have done now, we have taken the part of the second Brillouin zone which goes outside the first zone. We will transfer it into the first zone using the reduced zone scheme. So we will transfer the parts of the second Brillouin zone into the first zone, and similarly the third zone is based on the next nearest neighbors like described by the reciprocal lattice vectors G3. So these are the parts of the third Brillouin zone as shown here, and they will also be reduced into the first zone, and this is what we have done here. So if you have a Fermi surface, a Fermi sphere, you know that for free electron model the Fermi surface is in the form of a sphere. So depending on the number of electrons, free electrons in the solid, the size of the Fermi sphere is determined. You can say that the radius of the Fermi sphere depends on the number of free electrons available in a solid, because this number is different for different solids. So we will have different size of the Fermi sphere for different solids. This is a typical Fermi sphere as shown here, and you can see that the part of the Fermi surface in the first zone, and there are few portions in the second zone of the Fermi sphere. Similarly, the Fermi sphere extends to third zone, etc. So this is the part of the Fermi sphere which is in the first zone. You know that the entire first zone is filled with the Fermi sphere. However, the second zone has these bits 2a, 2b, 2c, 2d. So when we reduce these bits into the first zone, we get this picture. So 2a, 2b, 2c, 2d. So this is the second zone as filled by the Fermi sphere. Similarly, the third zone as filled by Fermi sphere. So here is the more correct picture. This is the filled space in the first zone, this is the filled Fermi sphere in the second zone, this is the filled Fermi sphere in the third zone. Okay, in the first zone we have the continuous sort of filling, but in the second zone we see that some part is filled, and in the third zone, but it is connected. In the third zone, these are the parts, corner parts, which come into the third zone of the Fermi sphere and as reduced into the first zone. So when we transfer these parts once again using the reduced zone scheme, we get these stars like this. So figure 8, the free electron Fermi spheres of figure 5 as viewed in the reduced zone scheme. The shaded areas represent occupied electron states. Parts of the Fermi sphere fall in the second, third, and fourth zone. The fourth zone is not shown here. The first zone is entirely occupied, and figure 9, the Fermi sphere surface on the third zone as drawn in the periodic zone scheme. The figure was constructed by repeating the third zone. So you must go through these pages over here, and when you come to the nearly free electrons, we have certain modifications. We have to round off these corners, etc., when we go to the real solids. So go through these pages. Let me show you these pages. Let me mention these pages which you will have to follow from this chapter. The page numbers, okay, this is the page number 223 to the page 230, and here is the Harris construction, which gives us a very easy way to find the parts of the Fermi sphere filled in the first, second, third, fourth, etc. zone. So Harrison construction of free electron Fermi surfaces on the second, third, and fourth zone for a square lattice. The Fermi surfaces encloses the entire first zone, which therefore is filled with electrons. So what we do in Harris construction, we take the radius of the Fermi sphere and we draw circles. Okay, so these are the circles making each reciprocal lattice point as the center. So we draw all these circles with radius equal to the radius of the Fermi sphere, and we get this type of situation. Now, if you have an area which is just one common area, like this one, this one, this one, this one, this one, so there is no overlapping of circles, and they will give us the part of the first zone filled by the Fermi spheres. And if there is an area which is common to two circles, for example, if you take this circle and this circle, so this is the area which is common to two spheres or two circles, so they belong to the second zone, the part filled in the second zone by the Fermi sphere. And similarly, if there is an area which is common to three circles, like this one, this one, this one, and this one, so that will represent the third filled part of the zone, this one. Okay, so that is the Harris construction. I hope you will go through the description given on these pages mentioned, and that concludes our syllabus. So a part of the chapter 9 early pages, few early pages must be seen before you can claim that you have covered the entire syllabus. Okay, there is a video, well, I will not give the video, but I have just mentioned today's lecture's video is video number 30. Last lecture which I gave previously, that was the figure 27. Sorry, so that was the video 27. So videos 28 and 29 are associated with the problems on chapters 7 and 8. I will mention the problems. I have selected few problems from these two chapters, and I have given the solutions of these chapters in my notes, which I will attach accordingly, and you will follow these descriptions in the PDF sort of form, and that will cover, you can say that will cover the lecture number 28 and 29, which is on the problems of the chapter number 7 and chapter number 8. So that completes our syllabus today, and I hope you will go through, and if you have any problem from any chapter anytime, you can always consult me, and I will be pleased to help you out of your difficulties. Okay, thank you very much, students, and I hope you will I hope good luck for you in the examinations. Okay, thank you very much.